Hi, my name is John Paul Raj, and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. On this particular video, we're going to be talking about the sum to infinity of a geometric series, aka the sum of the series. Let's start. The sum to infinity is a very interesting idea. You see, it comes from the idea of the nth partial sum. Sn, the nth partial sum, we've already seen in an earlier video before, is the sum of the first n terms, correct? So that's u1 plus u2 plus u3 all the way up till un. Okay, so if your un was an original sequence, the sum of the first n terms is denoted by this Sn, called the nth partial sum, also known as the series of that corresponding original sequence. So if the original sequence was an AP, an arithmetic progression, that would be the arithmetic series. And if the original sequence was a geometric sequence, then that Sn would be a corresponding geometric series. Now the question is, what would happen when n becomes really large, grows without bound, tends to infinity? The idea of limits comes into play, all right? In the case of an arithmetic progression, all right, for an arithmetic progression, what do we know of an arithmetic progression? We are always adding a term, whether it's a positive term or whether it's a negative term. The constant difference is going to be a constant difference that keeps adding on to each successive terms. So either the total, the sum, is going to grow large towards the positive direction, that means positive infinity, or that negative difference that we keep adding, that it's going to take the sum towards the negative direction or negative infinity. So for an arithmetic progression, as n approaches infinity, we say that the series will never converge. AP, that means an arithmetic series never converges. To converge means it doesn't go to a finite value, it's going to go without bound. So as n approaches infinity, Sn for an arithmetic series, Sn will also become infinite. The other word for does not converge is diverge. Let me put that also, okay? Diverge. Now, if you're an AP student, then you will study more about convergence and divergence. We'll talk about convergence and divergence of series in some other video, but in this case, I just wanted to throw in that word that we say that an arithmetic series will never converge, and the reason is because you're always adding a term. So also a geometric sequence, you might say, right? Because in a geometric sequence, you have a factor, and in fact, it grows faster than an arithmetic series, right? Because it's growing by a factor. But we have two different formulae for Sn for a geometric series, right? We have Sn is equal to a r to the power of n minus 1 over r minus 1. This formula is applicable when the value of r is greater than 1. Okay, absolute value of r is greater than 1. And then we have another formula which says 1 minus r to the power of n over 1 minus r when the value, the absolute value of r is less than 1. You know what? It's true that the geometric series will grow faster than the arithmetic series, but that's only the case when this absolute value of r is greater than 1. If that absolute value of r is less than 1, if you have a factor something like, r is 1 over 4, then it's a different story altogether. There and only there we say that a geometric series will converge. And what does it mean to converge? We said that as n increases without bound, guess what's going to happen? The sum of this geometric series will approach a finite value. And this finite value, that the geometric series will converge whenever the absolute value of r is less than 1. Only in that case, okay? When the absolute value of r is greater than 1, I already said it's not going to converge. So when the absolute value of r is less than 1, the geometric series will converge to a finite value. That value is what we also call the sum of the series. The sum of the series. So this idea, the sum of the series, is only applicable to a geometric series, not to an arithmetic series. And it's only applicable to a geometric series when that absolute value of r, that common ratio, is less than 1. Okay, this is what's called the sum to infinity. The formula for the sum to infinity, the infinite sequence, is given by Sn is equal to, or S infinity, not Sn, S infinity. Okay, S infinity is equal to a over 1 minus r. Again, those are the same terms. Okay, a is the first term and r is the common ratio. And as I said, that this formula is only applicable when that r, that absolute value of r is less than 1. Only when the common ratio, the absolute value of the common ratio is less than 1, we say that the geometric series converges, and it converges to this finite value, and that is called the sum of the series. Let's illustrate this formula using an example. Look at this question, all right? It says evaluate. That's it. It doesn't say anything about a GP, a geometric series. It doesn't say anything like find the sum to infinity, find the sum of the series, just says evaluate. And let's take this question, okay? It says 500 plus 450 plus 405 plus a 364.5 and then plus dot, dot, dot. That means the sum goes on and on. So we are just supposed to find the sum of this terms, 500 plus 450 plus 405 plus 364.5 plus dot, 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 dot. That dot, 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 dot literally gives us the hint that this sum up to infinity. That's the only clue we have. But we don't know that this is a geometric series, and only after we establish the fact that it is a geometric series can we use that formula for the sum to infinity of a geometric series, and that too, if the value of r, the absolute value of r is less than 1, only that time is that formula applicable. So let's go one step at a time, okay? So what are the terms of this sequence before it's made into the series with that plus, 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 that addition sign, the sum, okay? So the original sequence would have been something like this: 500, 450, 405, 364.5, so on and so forth. And how do we show that a particular sequence is a geometric sequence? Well, ratio of consecutive terms, right? So let's take the ratio of the second term to the first term. 450 divided by 500. This should be that 0, and this is 9, and that's 10. And so that ratio should be 9/10. As always, I always tell students, leave it as a fraction. It's okay. All right. Now let's take the ratio of the third term to the second term. It's a good habit to check each consecutive term so that you know that it's a common ratio, and because any two numbers when you divide, you're going to get a ratio. It needs to be a common ratio. Okay, so let's do that for the third term to the second term. So what do we have? We have 405 over a 450. Can you see this color? All right, it's a little faint, but that'll do. Let's try and divide this. Okay, so this is 5, 8, 5, 1, 5, 9, and that's 0. And that's 9, 9, and this is 9, 10. Again, we've got the ratio as 9/10. So the ratio of the second term to the first term is 9/10. The ratio of the third term to the second term is also 9/10. Let's go ahead and find the ratio of the fourth term to the third term. Even though that's a decimal, don't worry about it. Let's see, 364.5 over 405, all right? The first thing I'll do is that get rid of that decimal point on the numerator by multiplying the denominator by a factor of 10. So I get 3645 divided by 4050. Let's see what will happen when I divide by, let's say 5, all right? So this is 5, 7, 35, 36, 5, 2, 10, 45, 5, 9, all right? So here we go, 5, 8, 40, 5, 1, that's 0. This should go by a factor of 9. Yeah, it should. So this is 9, 8, 72, 9, 1, 9. And this is 9990, and this is again reduces to, I thought it reduced to something like that. Okay, never mind. So that's 99 and 910. Again, we can see that the ratio of the fourth term to the third term is also 9/10, and we can say that this is a GP, and the common ratio of this GP is 9/10. Verified, okay, verified. And we can also write down that this R, this common ratio, is less than 1. All right, now because this is a GP and because the common ratio is less than 1, we can use the formula of the sum to infinity. You can say, therefore, the sum of the series is A over 1 minus R. A is the first term. The first term is 500. So just put that value there. That's 500 over 1 minus R. R is a 9/10. Let's just simplify that. We keep that as 500. This is going to be equal to 10 minus 9 is 1 by 10. This is going to be equal to 500 times a 10, 5,000. Can you see my work? Yeah, you just saw that. Okay, so that is going to be the sum of the series that was given by 500 plus 450 plus 405 plus 364.5. You can see that it's like a decreasing sequence of numbers, but when you keep adding, because that R, that common ratio, is less than 1, even if it was a negative R, but that absolute value of R is less than 1, you can tell if it's a geometric sequence, okay? If it's a geometric sequence, and if that R, the common ratio, is less than 1, that geometric sequence will converge converge to one finite value as we saw here. Okay, so even though it's a sum, we are adding terms. Actually, we're adding very small terms, small factors. Okay, so it converges to one finite value. In this case, that value is 5,000, and that 5,000 is called the sum of the series. All right, now let's do one more question. Okay, one more question with a decimal point, just a different question. Let's take this question. This is 3 minus 0.3 plus 0.03 minus 0.003. So it's alternating in signs. That's number one. And then there's these decimals. Let's write it down here. Okay, I'll write down the series here. So this is example 2. And what do I have? I've got 3 minus 0.3 plus a 0.03. I believe that's the pattern. Yeah, and then a minus 0.003. What else do I have? Yeah, it goes in the same fashion. And then a plus 0.0003 and plus so on and so forth. Can you guys see this question? This is the question, all right? Interesting, right? The first thing I do when I see decimals is that I know I'll just get rid of the decimal by, multiplying the denominator by a factor of 10. So let's see what that'll happen. This will make this term, the first term is just 3. The second term will be 3 over 10. The third term is going to be plus 3 over 100, right? And the fourth term is going to be negative 3 over 1000. And as you can see, the fifth term would be then 3 over 1 followed by 4 zeros, and that pattern continues. So it's alternating in signs. That means this one should be a negative sign here. It's alternating in signs 1, and as you can see, there's a pattern in the denominator. It's a factor of 10. So if we can rewrite that as 3 minus 3 over 10 plus 3 over 10 square plus 3 over, that's a minus, sorry, 3 over 10 cube plus 3 over 10 to the power of 4. Now you begin to see the pattern, right? You can begin to see the pattern. Here, what we can say clearly is that when you look at it, you can see that it's the first term is 3. No doubt about that. The ratio of consecutive terms, that's what we need to demonstrate, all right? So we can say, what's the ratio of the second term to the first term? Well, that's negative 3 over 10 over 3. And when you work it out, negative 3 over 10 times a 1 over 3, giving you that the ratio is going to be equal to negative 1 over 10. Okay, now for the sake of time, what I'm not going to do for everything, but you need to check. Let me do one at least. Okay, so let me take at random the ratio of, let's say, these two terms. Is the fifth term to the fourth term? 1, 2, 3, 4, 5. Yeah, fifth term to the fourth term. Let's do that. Okay, so I have 3 over, that's how many zeros? It's 4 zeros, I believe, divided by a negative 3 over 1000. Okay, so what do I have? 3 over, that's 10 to the power of 4 multiplied by 10 to the power of 3 over 3. Okay, there's a negative 3, by the way. So those factors of 3 cancels off, and you will get, even here the 10s will cancel off. So you get negative 1 over 10 again as the ratio of the fifth term to the fourth term. And if you check for each successive terms, you'll get that the ratio is a common ratio. And we can say that this is a GP with R equals a negative 1 over 10. So the original sequence, okay, this was a geometric series. Remember, whenever we're adding the terms, it's the nth partial sum or the series, but the original progression is a geometric progression with R equals negative 1 by 10. And therefore, the sum of the series exists because the formula is applicable whenever the absolute value of R is less than 1. And in this case, even though R is equal to negative 1 by 10, the absolute value of negative 1 by 10 is less than 1. So we say the sum of the series, this series, is therefore A. What was A? A was 3 over 1 minus R, 1 minus a negative 1 over 10. Okay, and then that when we simplify, you'll get 3 over 1 plus 1 by 10, and that's going to be 3 over that's 11 over 10. So this is going to further simplify as 3 over 1 times 10 over 11, or 30 over 11. So this is the sum of the series, that geometric series. Well, they had not given us that it's a geometric series. They just gave us this question like, we valued this sum like 3 minus 0.3. We had to identify the pattern being that it's a geometric sequence, the original sequence being a geometric sequence, and this is the corresponding geometric series, the nth partial sum of that original geometric sequence, giving us this geometric series. And we identified the R, okay? To establish the fact that it is a geometric progression, you have to show that there is an R, there's a common ratio, And when the absolute value of that ratio is less than 1, only then the geometric series converges, and it converges to what we call the sum of the series. If you found this video useful, do not forget to like, share, and subscribe to this channel. I'm going to see you all in the next video.